little bit more into why are they the way they are, why is the error the way it is, that kind of stuff. Okay, so we'll talk about that in time, but just to give you the heads up, NUIM, you will have a class test on the Friday. I might run the DCU at the same time as well. We'll have to discuss that. In addition, NUIM, yesterday fortnight, so the day before the class test, I am their presentations. Part of the assignment is the groups have to make a presentation. So I will schedule that with the DCU people again offline. We'll find out when we can do that. NUIM people, we've decided to do that on the morning of the day fortnight, 2 weeks from yesterday in the morning time, about 10:30 or so. You'll be required to give a presentation as set out in the assignment, and then you will be interviewed. So I'll be interviewing the team members in a group and individually, and the purpose of all that is for me to satisfy myself that everybody in the group has contributed and contributed fairly, and that everybody understands everything that was done, and it wasn't just one bright spark who did all the work and everybody else just whatever, bought him some pints or something. So I got to convince myself that everybody contributed. So that's the purpose of that, okay? Thursday fortnight, yesterday fortnight for the NUIM people, and again I need to offline with the DCU people and see when can we do it. Okay. Dennis 2 through 16, I'm just going to mute your mic. You're probably doing some tests on the audio. I'm going to mute you if you don't mind. Mute yourself if you need to unmute yourself, but just I try and mute it just to cut down the ambient noise. So by all means unmute yourself if you need it for your tests. Okay, what else do I need to announce? That's pretty much it at this stage. So I'll see the NUIM students on Monday and start thinking about this class test. Okay, so has anybody any questions about that? Anybody here in DC, any questions about all that stuff? NUIM? Anybody over in NUIM? I lots of Dennis's. Dennis 10, 11, 12, 1, 2, 3, 4. If there's any students over there, you can send me a chat if you have any questions on anything I've just said, okay? David says yeah. Okay, so I presume yeah means you're happy rather than you. So let's start handout number 1, numerical differentiation. What's all this about? So you guys are all familiar with the concept of differentiation. You've known this for many, many, many years at this stage. Your leave cert and your French equivalent. Second one I learned about differentiation. And what differentiation tells us, if you have a function, the derivative of the function allows us to very precisely specify the rate of change of the function. So the function output tells us the value of the function. The derivative is what's happening to that value. Is it increasing or is it decreasing or is it staying the same in the vicinity of that input? So consider x squared minus 3 as an example. We all know df dx is equal to 2x. Just do that from the simple rules of differentiation that you all know. So df dx itself is a function. 2x df dx, we can work it out at a particular input. So for example, df dx at x equals minus 2 is equal to 2 times minus 2 or minus 4. Df dx for the input x is equal to 0 is equal to 0, and df dx at the input x equals 2 is 2 times 2 or 4. So we see df dx is a function in its own right. For various inputs we get different outputs. Now what these different outputs tell us is that its rate of change varies depending on the input. So in the vicinity of input x equals minus 2, the function f is varying in a particular way. It happens to be decreasing. In the vicinity of x is equal to 0, function f of x is neither increasing nor decreasing. It has a rate of change of 0. In the vicinity of x equals 2, the function f happens to be increasing with a rate of 4. So we can see the value of the derivative, df dx, to function in its own right, so it's from input to input. We know from forever, since we've been doing this for years and years and years, if the derivative is negative, if df dx is negative, it means that the function f is decreasing in the vicinity of that input. If the derivative is positive, it means the function is sorry, that should say increasing. That's a typo, that's me cutting and pasting. So that should say increasing if the derivative is positive. Then the function is increasing as you have the point. So I'll change that in the notes. And if the derivative is 0, then the function is constant in the vicinity of that point. It means you either have a local maximum or a local minimum. So here's a wee little function with x squared minus 3. It's a typical quadratic U-shaped curve. And we see for different values, here's input 2, input 0, input minus 2. Function value at minus 2 is equal to 1, x squared minus 3. Function value at input 2 is equal to 1, x squared minus 3. Function value at x equals 0 is equal to x squared minus 3 and minus 3. So we get this U-shaped curve. And what we notice is that in the vicinity of input x equals minus 2, the output of this curve is going downwards. So the function output is smaller. In the vicinity of x equals 2, input x equals 2, the function output is increasing. So the output is getting larger. And in the vicinity of x is equal, we're at a local minimum. In the immediate vicinity, were we to zoom in and zoom in and zoom in to an infinitesimal small window around x equals 0, this function would locally resemble a flat horizontal straight line, indicating that the function is neither increasing nor decreasing in that immediate vicinity of x is equal to 0. And these observations are mirrored or backed up by looking at the derivative. This picture here on the right-hand side is the derivative. If this is x squared minus 3, this is 2x, the derivative. And we see for input minus 2 over here, we see the function is f dash of minus 2 being negative. Over here, we've got the function increasing in the vicinity of input x equals 2, and that corresponds to the derivative f dash 2 being positive. F dash 2 is equal to 4 over here. A positive derivative corresponds to an increasing function. Here, the local minimum point corresponds to a derivative of 0. F dash 0 is equal to 0. So I've got another typo. Oh my God, typos already. 2 slides in and 2 typos. Apologies, that should say f dash of 0 is equal to 0. Too busy cutting and pasting. So I'll amend those in the notes as well. So where the derivative is equal to 0, f dash 0 is equal to 0, that should say, not 4. I was just obviously cutting and pasting. Derivative equal to 0 corresponds to a local minimum here. Okay. So you know all that. You've seen all that before, and you know everything I'm going to show you in this slide as well. For differentiating functions, you know the product rule, you know the chain rule, you know logarithmic differentiation, all these different techniques you've used, differentiation from first principles, etc., all can be used to differentiate functions. However, many practical functions that you encounter in engineering are and cannot be differentiated analytically. So these rules, product rule, chain but you might be working with some law, some physical law, which doesn't deal with the function, it deals with its derivative. So you have to work out the derivative of a function, but you don't know what the function is. So how can you differentiate a function if you don't know what it is? So in both these cases where you don't know the function, or the function is very, very complicated, we can't use the rule and the chain rule and all these things. So instead we use ways to numerically estimate the first derivative and higher order derivatives as well. And this is what this. So here's an example. Here's a current flowing through a capacitor, and the current is equal to the capacitance times the time rate of the voltage. Someone's come along and made some measurements at time 0.1, 0.2, as far as 0.9. The voltage at these particular units of time, or these samples of time, are given by these values here. We don't have the underlying function, Vt. We don't know what Vt is. Is it a sine function, a cosine function? Is it an exponential function? All we have are samples. But in order to work out the current, we need to be able to work out the derivative of the voltage. So how can we work out the derivative if we don't know what the function is? Okay? All we have are samples. Well, again, we can use numerical techniques, as we're going to learn in this handout. Because numerical techniques don't need to know the form of the function. They just need function outputs at sampled inputs. Once you have these sampled inputs and sampled outputs, you can combine them in various ways to estimate the derivative. And that's what we're going to do. Here's another engineering example. Here's a case where someone fired some radar at an airplane, and they would like to work the radar cross-section or the radar return from the plane. And in this case, well, you're trying to work out the electromagnetic field that returns to you from a radar, and you don't know what it is. So how can you work it out if you don't know what it is? Well, it's governed, whatever the radar return is going to be, it's going to be governed by Maxwell's equations, and Maxwell's equations express time in terms of derivatives. Time derivatives of the electric field and the magnetic field, and spatial derivatives. And you've got the various Maxwell's equations that you guys have all seen. The problem is we're applying these Maxwell's equations to fields that we don't know. We're trying to work out the field. We know they obey these equations, which are expressed in terms of derivatives, but we don't know what the electric fields are. So finite difference solvers or numerical solvers, such as what was used to make this picture here, take the unknown functions and sample them. They say, well, here is a vector containing samples of this unknown electric field or this unknown magnetic field. We don't know what they are, but we're going to make a little placeholder and put samples in there. We're going to sample it through space and through time. And then we express these physical laws, which are expressible via time derivatives and spatial derivatives, by combining these sampled values in various ways, according to the simple numerical rules we're going to put together here. And you can do that, and you can solve for the problem. You can apply some boundary conditions and initial conditions to make yourself a nice picture of your radar return. Okay, so this is a very famous technique in electromagnetics called the finite difference time domain. If you go into Google and type in finite difference time domain, you will find a whole body of work and a whole body of commercial solvers solve Maxwell's equations, and as the name suggests, it uses what's called finite difference. It takes Maxwell's equations, which are expressible via derivatives. It recognizes it can't do those derivatives because you don't know what the functions are, so it uses finite approximations. Okay, so that's what we're going to learn about here. So you can make nice pictures out of all this stuff. Okay, so a word about notation. A little bit topsy-turvy because we've been using this notation in previous weeks, but let's just remind ourselves of the notation we're using. F of x is a function. It has a specific value f evaluated at x0, specific input x0. The derivative of f of x is a function. We denote that function by df dx. Okay? df dx evaluated at x equals x0 at the specific input x0. That's one way of denoting that. That's the df dx is a function at the specific input x equals x0 takes on this value here. So that's what this means. And we'll see some alternative notation later on. Let's use examples. Again, just to remind ourselves what we're talking about. Here's f of x is equal to e to the sine x. It's a function. It takes in inputs, gives outputs. The chain rule tells us that the derivative is equal to the derivative of e to the sine x multiplied by the derivative of sine x. We apply the chain rule. This is a composition. It's of the form f of g of x, where g of x is equal to sine x, f of x is equal to e to the x. Composition gives us that, and the chain rule gives us this. So, for example, this is a function. This is a derivative of this, and it takes on the specific value when x is equal to 0. The rate of change of this function around the input x equal to 0 is obtained by putting 0 in here. We get cosine 0, e to the sine 0, which is 1 times 1, which is this notation, df dx, is a little bit cumbersome. So if we're deriving expressions, this gets a little bit cumbersome to write. So we use two alternative notations, which just mean the same thing. That's what alternative means. They mean the same, so it's a little bit easier to work with. The first alternative notation we use is that df(x) evaluated at the input x equals x0 is called f dash x0. Okay, so we've all seen this before. I've been using this notation already, so again, this is just to reinforce what we've already done. The second derivative evaluated at x equals 0 is denoted f double prime x0. So this double prime just means take the derivative twice and then apply it at x0. Third derivative given with 3 primes and so on. This prime notation, f prime, f double prime, f triple prime, etc., gets a little bit cumbersome for higher order. If you had to do the 7th derivative or the 8th derivative, you'd be putting 7 or 8 little primes in here. It gets messy. So instead, generally, once you get to about 3 or 4, third or fourth derivative, people often use this kind of notation instead. So for example, the fourth notation, or the fourth derivative, denoted by f to the power of bracket 4 x0. This is not f raised to the power of 4. This means the fourth derivative of f. That's what the brackets mean. If there wasn't brackets there, it would be f to the power of 4. The brackets mean the fourth derivative. So this just means this, okay? So two alternative notations, we can use these primes, or we can use these little numbers and brackets. And I use both. And sometimes I'm not consistent. I try and use the primes for lower order and the numbers for higher order, but sometimes I forget and I use, I might call the first derivative f bracket 1, for example. But it all means the same. Okay. So back to derivatives. Recall that the definition of the first derivative of x is given by this limiting process here. To get the first derivative, what do we do? So the first derivative evaluated at x. Well, you take x and you add a little bit to it. So you look at x, the input x plus some little increment. So some input value in the vicinity of x plus a little. And you work at the function value evaluated at this. Then you get the function value evaluated at x. You get the difference between the two. This gives you the difference in the output as you increase the input. And on the bottom you have x plus h minus x, which is just h. So on the top we have the difference in the output, and on the bottom we have the difference in the input as we increase the input by a little bit h. Okay, and this gives us a ratio of how quickly the output changes versus how quickly the input is changing. And to be technically correct, we do this for vanishingly small h. We take the smallest h we can possibly imagine, an infinitesimally small h. H is equal to 0, 0, 0, 0, the smallest possible number you can think of, but not equal to 0. Push 0. We can creep up to 0, get as close to it as we can possibly get. That's what the limiting means. Now, many functions in engineering pose difficulties because it's difficult to do this exactly, either from first principles or via the chain rule or the product rule or the various other rules, all of which are equivalent to this. So what do? Well, we can approximate it, and the simplest thing we can do is to say, well, if we can't do this limiting process exactly, if we can't work out this ratio of the change in the output versus the change in the input for infinitesimally small h, the next best thing we can do is take a very small h, not infinitesimally small, but small, and plug that in here and work out the change in the output compared to the change in the input and measure that. And this will be approximately this. Okay? It's only approximate because to be exact we'd have to take an infinitesimally small h. We're not taking an infinitesimally small h, we're taking a small h. So this is only going to be approximately equal to this. But it's going to be a reasonable approximation as long as h is small. So by this stage of course, hopefully you've realized that part of what we're trying to do in this course is rather than just using this approximation, which is called the forward difference approximation, rather than just using it, it's very simple to use it. What we're hoping to do is to qualify exactly what a statement like as long as h is small means. How small does it have to be? What is the error in this compared to the size of h? How small does h have to be for a given desired level of error, etc. Okay? So if this is one thing, that's very easy. Okay? Your granny could apply this. What we're hoping to do is to qualify this and work out, is this a good approximation? Can we make it better? These kind of questions. Okay. It's called the forward difference approximation for obvious reasons. We take the input x, we're trying to work out the derivative evaluated at x. We take x and we increase x in the forward direction. In other words, we add a little increment to x. So we make this a little bit bigger than x, so it's a forward step. Okay, so this is what we're doing. Here's a picture, kind of a generic picture. The black curve here is a function. Inputs on the x-axis, outputs on the y-axis. And what we're doing is, here's x is 0. We would like to work out the derivative of the function, the black curve, at the point x0. And at the point x0, the function value is f of x0, denoted, so the point on the curve is the orange dot here. So what we're doing is we're saying, well, we're trying to work out the tangent to the curve at this point. And we approximate the tangent to the curve by taking not x0, but x0 plus h, where h is a small increment. That gives us this point here. We work out what is the function value at x0 plus h. That gives us this f of x0 plus h. So we're at this point on the curve. The orange point is the point x0 plus h, f x0 plus h. And we approximate the tangent by this line here, the hypotenuse of this right-angled triangle. And when we say, our guess is that the tangent to this curve has the same as this line here, the hypotenuse of this triangle. The actual tangent doesn't have the same slope, but it's just small. This should be a good approximation to the tangent. Okay. So what is the slope of this hypotenuse? Well, the slope is just the tan angle it makes with the x-axis, which is tan of phi, which is the opposite, which is the difference in the two outputs.
Barely anyone listening.
Zero. But
Or you're amazing. You want the audio.
the difference in the outputs divided by the difference in the inputs. That gives us tan of phi. Okay. And the idea of the finite difference is that's going to give us a reasonable approximation to the slope of the actual tangent. But as we make h smaller, we move our way down the curve, down closer to this point here. As h gets smaller, and as h gets smaller again, this hypotenuse becomes closer and closer to the actual tangent. And in the limit, as h goes to 0, this hypotenuse and the tangent are the same. Okay, so the idea is this is geometrically what we're doing in the finite difference approximation. We're taking an increment h, we're making this little triangle, we're getting tan of this angle phi, and we're saying tan of phi is equal to the slope of the tangent. And we're hoping that this hypotenuse here of this little triangle is the same as the tangent. It's not quite, but it gets better and better and better the smaller we make this triangle. Okay, great. So let's do an example. Consider the function of x is equal to e to the minus 2x. And we would like to compute the derivative at the point the input x is equal to 2. Now obviously we know how to do this exactly using numerical method for this. We know the answer. We know that the answer is, again, applying the chain rule. It'll be the derivative is minus 2 e to the minus 2x. So at the specific input x equals 2, we're going to get minus 2 e to the minus 4. Okay, whatever that is. But instead what we're going to do is we're going to use a forward difference approximation, which is f of x plus h, which is this thing here. We put x plus h into this rule. We get e to the minus 2 multiplied by x plus h. From that we take away f of x, which is this. We divide by h. And let's examine how accurate we can make this. Let's examine the effect of changing h. We know from our little geometrical argument there that the smaller we make h, this should get closer and closer to the actual answer. We know the actual answer is minus 2 e to the minus 4. So let's examine the effect of changing h on in the region. Actually, sorry, what I've done is specifically at input x equals 2 and more generally in the input interval 2 to 3. So let's plot this thing, not just 2, but actually between 2 and 3. And then let's plot this, the derivative, the approximation, the forward difference approximation between 2 and 3. This is what we get on x-axis, inputs between 2 and 3, on the y-axis, the derivative. The exact answer is given for various inputs between 2 and 3 here in red. And we see the blue curve is the value of the derivative when h is equal to 0.1. We see it's pretty close to the red curve. And by making the step size 10 times smaller, we get the black curve, which is even closer to the red curve. So as h gets smaller, by a factor of 10, the approximate derivative given in black gets closer and closer to the actual derivative given in red. So that's just visually confirms what we expected. We expect that as h gets smaller, this approximate value, the forward difference approximation, should get closer and closer and closer to the real, and it does. Again, that's a little bit unsatisfactory. Can we quantify more closely exactly how close it gets? How small does h have to be? So this is this is useful to us. But if I were to ask you, how small does h have to be such that we're within 1%? Or how small does h have to be such that we're within 10% or 0.1% or 0.001% or some desired threshold of accuracy? It's not immediately obvious to know what h you should use. Okay? All we know and all this picture tells us is that h gets smaller, we get better accuracy. So to delve into this a little bit more, let's look at the specific value f dash at 2. So at the start of this, f dash of 2 is equal to about minus 0.00352 or so, or maybe 36, maybe somewhere around there. So we know, oh, this is the answer here. This is the exact answer for f dash 2. And let's work out the 4 different estimate for varying values of h. So as h gets smaller, h equals 0.1, 0.01, 0.001. Our answer gets closer and closer to the desired answer. Here we're right to about 2 decimal places. Here we're correct to about 3 decimal places, 4 decimal places, and so on. We get closer and closer and closer to the exact answer. So by the time we have very small h, 0.0000001, the last row here, our answer f dash 2 estimate is very close to this. Okay. Still, we haven't really learned much here. All we've done here is confirm that as h gets smaller, our answer gets better. But let's look at the error instead. So the error, this is the estimate. Let's take the estimate away from the actual answer and make a little table here with the error itself. So here is the different step sizes, and here is the error. And can anybody tell me, well, here's the answer, but we have an interesting pattern emerging. So the interesting pattern that emerges is that the error has a very definite behavior. As h gets smaller, a factor of 10, the error decreases by a factor of 10 each time. And that the error, as h gets really small, the error begins to resemble minus 0.037h. So in each of these cases, the number on the right-hand column is approximately equal to the h value in the left-hand column multiplied by minus 0.037. Okay, so this here, the last one, is pretty much equal to this for minus 0.37 and so on for this. So there's a very definite structure there. The error doesn't increase in an arbitrary fashion. It doesn't just get smaller in some random fashion. The error gets smaller in a very, very structured manner. And it's suggestive that the error in the forward difference operator for this particular example is given by the step size by minus 0.037. Maybe that was a coincidence. Maybe that was just a product of the particular function we were looking at. So let's get some data for a different function. Let's look f of x is equal to sine of 3x. It's a different function. Different input. Let's look at x0 equals pi over 4. You can work out the derivative is going to be 3 cosine 3x. Evaluated at pi over 4, we're going to get 3 cosine 3 over 4, whatever that is. And we work it out numerically using different h samples in our forward difference approximation again. So we're using the forward difference approximation using correspondingly smaller h's, and we work out the error between the exact answer and whatever we get. And again, we see this pattern. We see that as h gets smaller, epsilon f gets smaller in pretty much the same way. And we see as h gets very small, the error becomes approximately 3.178 times h. So again, in this example, this is a completely different function. Again, we see as h gets smaller, the error turns out to be some constant times h. The constant is different than what we had here. We don't expect the constants to be the same, but the overall pattern is the same. In both cases, the error is equal to the step size multiplied by some constant. So from that, we can maybe conclude or hypothesize, and conclude it yet, we've only looked at 2 examples, but we can hypothesize that for small h, the forward difference approximation gives us an error equal to step size h multiplied by some constant, whatever that constant may be. And we've got evidence to suggest that's the case. Let's prove that that is the case. Let's prove that the forward difference approximation does give us an error of this form. How do we do it? Well, here's my question. Well, why is this? Before we go and prove it, Why does it have this form? And what is alpha? In this particular example, alpha was 3.178. In the last example, alpha was, whatever it was, minus 0.037. What is alpha? What gives us those numbers? How would we prove it? Well, again, first thing we reach for is the Taylor series. When you're doing numerical analysis, the Taylor series is your friend. It's the first step for analyzing all these things. Okay, so the Taylor series tells us how to analyze these things. We know what it is. We've discussed this before. It's a way of approximating a general function, such as sine 3 of x, in the last example, as a polynomial of some specified degree. We know that the Taylor series, it expands around an expansion point. The series is, or the approximation is exact at the expansion point and decreases the further away you go from that. We know that. We did some of that before. And this is the form of it. The function we're trying to expand in a Taylor series, f of x, we can write it as f evaluated at the expansion point plus the derivative at the expansion point multiplied by the difference between, that should be x minus x0. Apologies, it's the other way around. A third mistake in these notes, oh my god. And this should be x minus x0 and this should be x minus x0 squared. And this should be x minus x0 to the power of n. So I have these the wrong way around, so apologies. I'll fix those. And so on. We can't do an infinite number of terms suggested here. So we generally truncate and we say a Taylor series polynomial approximation of degree n, where we take it to n terms. Okay, and again, these should be the other way around, x minus x0 rather than as I have it here. I'll change that and I'll put it professional. So, how is that of use to us? Well, we can write x, a general point x, as the expansion point plus h, and that enables us to write f of x is equal to f of x0 plus, this should say, or this is what we did have. We can write that as f of x0 plus h is equal to f of x0 plus h times f dash x0 plus all this stuff. These are equivalent. Okay, this is just a reordering. Okay, so this is the form of the Taylor series we're going to use. So why is this useful to us? Well, let's take this expansion for f of x0 plus h, and we can write it as the first two terms, which is a linear approximation, plus all these higher order terms that we can forget about. Ignore the portion in red, all these higher order terms, and just take the first two terms of our Taylor series, the linear terms. Ignore all guys in red. We can rearrange that. Well, this is what we get. We get that f of x0 plus h is approximately equal to this. And we can rearrange that. We can bring the fx0 over here. We can divide by h. And we get this. F dash at x0 is approximately f of x0 plus h minus f of x0 over h. And we recognize this as being our forward difference approximation. This is what we derived a few slides ago. Okay? Just from the formal definition of a derivative, we came up with the forward difference approximation. We've derived it again, this time from the Taylor series. Okay, but this time we've derived it in a more useful way, as we'll see in a second. So this is just our forward difference approximation that we've been using in these examples. Okay. This is just an alternative way to derive the forward difference approximation in this center expression here. It's a useful way of deriving it because the Taylor series expansion enables us to work out the error, because we know we got this by neglecting a whole bunch of terms in red that we ignored here. So we can look at these terms in red and we can say something about the error, because the error is caused by our neglecting all of these terms in red. So let's do the error analysis. So we know from our experiments that the finite difference approximation gets better as h gets smaller. Can we say something more specific than this? Well, let's say epsilon f is the error, okay, that we've been examining experimentally. The epsilon f, the error in the forward difference approximation, is the actual derivative minus this term here, which is the forward difference approximation. The difference between the two is the error. And we know that's equal to the term in red, not quite equal to the term in red, but it can be derived from the term in red that we neglected 2 slides ago. Okay? So we can take the term in red and just divide by h. We get this here. So this is our error. And what we see is, for h small, this error term, the difference between the exact f dash x0 and the finite difference approximation, it's an infinite series of terms, but for h small, it's dominated by the first term. As for h small, h is small, but h squared is minuscule, h cubed is infinitesimally small, and so on. So this is the error. For h small, it's dominated by the first term, so we can approximate our error in our forward difference approximation by this first term. We can say the error in our forward difference approximation is equal to minus h over 2 f double dash x0. In our numerical experiments a few pages ago, we came up that the error was equal to alpha times h. Now it appears that alpha is approximately equal to minus a half times the second derivative at the point in question on our error analysis here. Where numerical experiments predicted that our error was of the form alpha h, our analysis suggests that alpha is equal to, what could we have multiplying h? We had minus 1 over 2 f double dash at the point in question. It tells us that our error in our forward difference approximation is of the order curly OH. So we've seen this notation before. It means that there is an error in the method. There's a whole infinite series of errors, but the most important error, the largest term in the error, is of the form h multiplied by a constant. That's the most important term of the error. All the other ones you can kind of ignore because h is small. All the other ones are very small compared to this leading term. It tells us as h gets smaller, the error gets smaller. We saw that. It tells us that the error gets smaller in a linear fashion. We saw that already. But now we know even more. It gets smaller in the form alpha h, where alpha is this particular term here, minus f double dash at the point in question over 2. So let's go back to our example. Here was f of x equals e to the minus 2x. At the input x equals 2, here's our answer. Here's our forward difference approximation. The error at input x equals 2, therefore, is equal to our forward approximation minus the actual answer, so the difference between this term and this term. At x equals 2, this would be minus 2 e to the minus 4. At x equals 2, the forward difference approximation would be e to the minus 4, e to the minus 2h minus e to the minus 4 over h. These are the numbers we got. We saw before that as h got smaller, epsilon got smaller, pretty much according to alpha h, where alpha was minus 0.037. We saw this already. But now our error analysis has told us something very interesting. It tells us that minus 0.037, rather than this being a random number, should be equal to minus a half f double dash evaluated at 2. And if you do that, if you take f, which was e to the minus 2x, wasn't it? Get the second derivative, evaluate that at 2. That's going to be plus 4 e to the minus 4. Divide that by 2, multiply it by minus, what do you get? You get minus 0.0366. So our error analysis using the Taylor series predicted that the error would go as minus 0.0366 h, and numerical experiments predicted minus 0. Pretty much 0.37. Okay, so our little numerical experiment and our error analysis based on Taylor series match each other, as they should. Let's look at this on a linear scale as we've done before. If this is h on the left-hand column here, and this is epsilon, if you plot this on a linear scale, it gets very hard to see because these are so small, it all gets crammed near the x-axis. You can't see it very well. So instead, let's plot log of 10 versus log of epsilon. Well, log of 10, we were decreasing epsilon by 10 times. We get minus 1, minus 2, minus 3 all the way down. Log of 10 of the error, the absolute value of the error, we're not concerned whether it's plus or minus error, it's the absolute value that counts. We can do that. Take the log 10 of absolute value of all these numbers here in the right-hand column. And we saw before that the error was approximately equal to alpha times h. Therefore, log of the error should be equal to log of alpha h, which is log of alpha plus log of h. So on a log scale, we should see, we've seen these kind of pictures before. Here is h on the x-axis, so h, log of h is -1, this corresponds to h equals 0.1. Log of h is -2, this corresponds to h equals 0.01. So each of these tick marks on the x-axis corresponds to h getting smaller by a factor of 10. So we can squeeze a whole lot of h values into a small amount here. On the y-axis, we have log 10 of the error. Okay, so this basically tells us how many decimal points of accuracy we get. 1 decimal point, 2 decimal points, 3 decimal points, effectively. So as we go down here, it corresponds to a smaller error. As we go to left on the x-axis, it corresponds to a smaller h. And I've plotted log 10 of h in red, log 10 of epsilon in blue, and we see, as predicted, one is equal to the other, just plus some constant, the constant gap being -1.43. And so again, did some numerical predictions, or some numerical experiments, got some data, got some error analysis which suggested the form that this error should take, and lo and behold, a numerical experiment matches what our error analysis told us was going to happen. Okay. Any questions about that before we plow on? We've seen that kind of stuff before, so hopefully this is beginning to make a little bit of sense to what I'm trying to show here. So what this diagram is telling us is that for this particular approximation, as we make h smaller, so as we move along the x-axis to the left, the error gets smaller, so we move along the y-axis downwards, which is a good thing. As h gets smaller, the error gets smaller, but it tells us that the error gets smaller in a very specific rate. As we decrease h by a factor of 10, the error will only decrease by a factor of 10. It will get 10 times smaller. We would rather that as h gets smaller by a factor of 10, we would rather see the error get smaller, not by a factor of 10. We'd like to see the error get smaller by maybe a factor of 100 or 1,000 or 1,000,000. Okay? So this is an okay method, but we'd like to do better. That's what we'll do. NUIM, have any questions over there? Is there anybody in NUIM listening to me at all? Martin's there, and Maeve is there, P.O. Regan is there, and Smythe is there. You all alive in NUIM? Send me a question if you have any questions, otherwise we'll move on. Okay, so what we would like to do. Standard thing, what we do in all these notes is we start off with something relatively straightforward, we explore it, and then we ask the question, how can we do it better? So we have a way now of computing approximate computing derivatives, and it's okay. It gives us an error, which is order h. So if you make h smaller, the error gets smaller, so it's not bad. But we'd like to do better. So how can we improve things? Well, one way of improving things, well, one way it might improve things, turns out it does, but let's see why it doesn't, is to, rather than using a forward approximation, we use a backward approximation. For the forward approximation, we had a picture like this. We had x0 where we were trying to work out the derivative, and we took x0 plus h. So we took a forward step. We took some other input to the right of x0 on the x-axis and worked out the difference in outputs versus the different inputs, and there you go. A derivative should work the same whether we take a step to the right or take a step to the left. Okay, so equivalently, what we could do is look at not x0 plus h, we could look at x0 minus h, this red point here to the left of x0 on the x-axis. We could work out the function value at f of x0 plus h. We could then draw this little triangle between this point and this hypotenuse in this triangle, we could say that is an approximation to the tangent at this point, and we could work out the slope of this hypotenuse and say the slope of this hypotenuse is approximately equal to the slope of the tangent, which is the derivative. So it's exactly the same trick as we did before, but rather than stepping to the right, we step to the left. And again, smaller we make h, the better this should be. And this is called the backward approximation for obvious reasons. Rather than stepping forward, we step backwards. How good is it? Is it going to be better? Well, using the Taylor series, we can write, well, if f of x0 plus h was given by the previous Taylor series, f of x0 minus h is given by the same Taylor series, but we saw a plus h before, we put in a minus h. So it's f of x0 plus minus h, which is minus h, plus minus h squared. Minus h squared is plus h squared. That becomes plus h squared over 2. Minus h cubed is equal to minus times h cubed. So we get this alternating Taylor series. Plus terms, minus terms, plus terms, minus terms. So a very similar form as before, but the presence of a minus here just makes every second term alternate. Okay. And again, we can derive our back difference approximation. We can forget about the stuff in red. They're all the higher order terms. We can keep a linear approximation. And we can rearrange the linear approximation. We can take f of x0 over here. We can leave f dash over here. We can divide across by h. And ignoring the terms in red and multiplying across by minus 1, we get this. This is our backward difference approximation. It's exactly similar to our forward difference approximation, just we use x0 minus h rather than x0 plus. And the term in red is key to understanding its error. Is it going to be good? So here we can plot it. So in the middle here we have the actual derivative. It's the same example as before. What was it? E to the 2x. In the region, e to the minus 2x rather, was it? E to the 2x. Whatever it was. In the region 2 to 3 inputs. The red curve here is the exact answer we could do analytically. The blue one above is the forward difference approximation. It's not too bad. That's for h equals 0.1, I think. The black one below is the backward difference approximation using h equals 0.1. Again, it's similarly accurate. It's okay. It tracks what we want, but it's not madly accurate. Can anybody see a breakthrough observation you can make about these two methods? So we can see the backward difference method is pretty much as accurate as the forward difference. They're both equally far away from the exact answer. Can anybody see an interesting observation that's going to help us? Manuf, can you over there? The question is, the red one in the middle is the exact answer. The one on top is the forward difference. The one at the bottom is the backward difference. They're equally close to the red one, so neither one is particularly better than the other. Can you see an interesting observation that could help us make some progress? Anybody? Why would you say the average of them? Yeah. So the comment here in DCU is that the forward difference is the blue curve, tends to, in this particular example, tends to overshoot the exact answer. The backward difference for this particular example tends to undershoot. So if you take the average of the two of them, so Kieran's saying, can you put the two of them together? Yeah, good man, Kieran. That's pretty much what we said here. The average of them together, hopefully these errors, one is a positive error, one is a negative error, and the average should cancel out, hopefully. It's not always the case that the forward overshoots and the backward overshoots. Sometimes it's the other way around. Sometimes the forward undershoots and the backward overshoots. For this particular example, it's the way it is, but it doesn't have to be that way. But in each case, it is the case that one of them overshoots and one of them undershoots. So the observation is right. They're equal and opposite errors, pretty much, or it looks visually at least that they're equal and opposite. So the average should be better. So let's look at the backward difference approximation and confirm that's the case. Here's the backward difference error, epsilon b for backward. Is the actual answer minus the backward difference approximation. This here is just equal to the term in red that we left out before. It's equal to all this stuff. This is an infinite number of terms in h. For h, very small, the important term is the first term. All the other terms we can ignore. And so we see that epsilon beta is approximately equal to this here. What we see that this is pretty much the same term. It's of the form alpha h as before, but the alpha in this particular case happens to be minus the alpha the last time. The last time we got minus this. Here we get plus this. And the reason it's minus is because in the Taylor series, remember the Taylor series had alternating plus minus terms. So the leading term here was a positive because of that alternation. The last time the leading term was negative. That's where the cancellation happened. So this error looks very similar to epsilon f. It's just equal to it multiplied by minus 1. So it's again of order order h, gets smaller in a linear fashion. So we haven't improved in the forward difference approximation, but this is equal to minus it. So let's look at let's take a closer look. We had epsilon f. This was the error for it. Here was a leading term, minus h over 2 f double dash, evaluate at the point in question, plus all this other stuff. Epsilon b backward was equal to plus h over 2. The first term was flipped. The second term is the same because it was only every second term flipped in the Taylor series. So the second term here, the f triple dash term, is the same, but the first term are equal and opposite. But if we add the two together, we come up with something better. If we add the two approximations together, the combined error will be the sum of these two errors. And the first term will cancel, and we'll get an error which is h squared. Because the leading terms will cancel. So if we add the two together, we're going to get a better approximation. Its error will be order h squared. That means as h gets smaller by a factor of 10, the error gets smaller, not by a factor of 10, gets smaller by a factor of 100. So much better. So how do we make that? Well, let's put the two Taylor series side by side. Here's the Taylor series we use for the forward difference on top, the Taylor series we use for the backward difference on the bottom. And if we add the two of them together, if we subtract one from the other rather, we get f of x0 plus h minus f of x0 minus h on the left-hand side. On the right-hand side, every second term cancels. First term cancels, the third term cancels, we're left with this stuff here. That means we divide across by 2h. We get this. On the left-hand side, we have this. On the right-hand side, we now have f dash x0 plus an infinite number of terms, the leading term of which is h squared over 6 f triple dash x0. So we can ignore the stuff in red and say summation for f dash is equal to this thing on the left. So we get a central difference approximation by ignoring the stuff to the right. The central difference approximation is the term on the left. It's an approximation to f dash. And we see the leading term in the error is not h multiplied by something, it's h squared multiplied by something. Which is good news. So again, for small h, the error will be h squared. So for h equals to 0.1, the error is 0.01 times the constant. So a remarkably simple way of improving the accuracy by an order of magnitude. Similar amount for the forward difference approximation, we got to work out a function value. Got to work out a function value, got to divide by h. So it's the same amount of work in your computer in terms of the amount of operations, but remarkably more accurate in terms of the actual answer you're going to get. So well worth doing. So the error is given by this. The error leading term is h squared multiplied by the third derivative. And it's going to be a lot better than the forward and backward approximations. And here's the example which shows it. So here's the example we saw before. Whatever it was, e to the 2x or whatever it was we were looking at. The red curve here is the exact answer. Again, the blue and the black are the forward and backward differences. And the yellow curve is the central difference. And it sits, at least visually, pretty much on top of the red one. So you can see it's much better, even just looking at it visually like that. So let's be a bit more rigorous about it. Let's look at the error precisely. Let's look for the particular input x equals 2. We work out for different values of h. We work out the actual derivative. We work out the central difference derivative. We take one away from the other to get the error. And we see the error goes like this. 0.1, we get 0.000244697.4. 0.01, this. 0.001, this, etc. And we see, roughly speaking, the pattern tends to be that the error in the central difference approximation is equal to h squared multiplied by 0.0244, where 0.0024 happens to be, from our error analysis, this number here that we're seeing in our experiment should be similar to minus the third derivative evaluated at 2 divided by 6 times h squared. So this 0.0244 should be equal to minus f triple dash 2 over 6. And when you work out this expression here, this is what you get. You see very close to what we're seeing numerically. Okay? So again, we've validated numerically what our error analysis suggests is going to happen. Using a log scale, what do we expect? Here's log 10 of h, here's log 10 of h squared. Will this be 2 times log 10 of h by the rule of logs? Here's the central difference. Again, my God, it's my 4th mistake in these notes. My God, someone fire me for God's sake. Epsilon c, someone making a note of all of these. Someone sending an email with all those mistakes. This is terrible. Epsilon c, this should say, for the central difference approximation. On a log scale, if we saw before the error is equal to h squared multiplied by a constant, we would expect the log of the error equals to log 10 of h squared plus a constant. Lo and behold, when we plot our graph, here's log 10 of h, the red line before. We saw that the forward approximation tracked this red line as the error, as the h got smaller on the x-axis, we moved toward the left. The error got smaller in the forward difference, but it tracked this red line, which meant that it got smaller at a certain rate. The central difference approximation, in contrast, tracks not log of 10, not log 10 of h, but log 10 of h squared, which gets smaller, the error gets smaller at a much more rapid rate. So for any given decrease in the size of h, the error drops much more steeply. Okay. And we see, as expected, log 10 of the error is equal to log 10 of h squared plus a constant gap between the two, which is what we expect from our error analysis, which would suggest that the error is equal to log 10 h squared. This is just twice log 10 h, plus some constant gap. Okay. Now, any questions about that? Take a break for about 10 minutes after, in a few minutes time, because hard going. So I'll finish off this handout, take about 5 or 10 minutes, and we'll take a break maybe for a few minutes. Any questions before I move on? NUIM, how are you? You all well? You still okay, Kieran? Maeve? Oh, well. Yeah, okay, good stuff. Okay, let's move on. Let's do something a bit different. Here was our Taylor series. This is how we derived the central difference approximation. We took the Taylor series for the point in question. We're trying to get the derivative at x0. We took a Taylor series taking x0 as expansion point and moving to the right, so positive h. Then we looked at the Taylor series taking x0 as an expansion point and moving to the left. That's the second equation here. And to get the central difference, we took one away from the other. What happens if we add the two together instead? Yeah, exactly. So if we add the two together, we're going to get cancelling every second term, but rather than the first and third terms cancelling, it'll be the second and fourth. So instead of all the odd terms cancelling, it'll be even terms cancelling. So if we add the two together, this is what we get. We get this plus this on the left-hand side, and this time we keep the odd value terms here. So the first term, the third term, the fifth term. The odd value terms corresponds to the even derivatives, the 0th derivative, the second derivative, the 4th derivative, and so on. So what can we do with this? Well, what we can do with this is we can take f of x0 over to the other side, divide everything across by h squared, and this is what we get. We get this construction here, the function values evaluated at x0 plus x0 plus a little bit, x0 minus a little bit. So this construction on the left is equal to the second derivative at x0 plus some higher order terms. So there should really be a dot dot plus dot 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 dot. So we can ignore the terms, the higher order terms on the right. Again, this should be plus dot dot dot. And we can make an approximation to the second derivative. So previously we made a central difference approximation to the first derivative. Now we can make a central difference approximation to the second derivative by doing this. Okay, so it's a similar expression as before, but it involves function values at x0 plus and minus h, and also at x0 itself, and 3 terms on the top rather than just 2. Okay. order is order h squared, as we see up here in the top equation. We see the first term in the error is given by h squared and is given by minus h squared over 12, the fourth derivative at the point in question, plus a whole bunch of stuff. So it's order h squared. Okay, so what have we learned? We've learned that sometimes it's difficult to make derivatives, so we need numerical ways of doing it. We've derived some very simple rules. The forward difference rule is a really simple rule, the backward difference rule. And they're pretty easy to apply. They're reasonably accurate. We've learned that a little bit of thought, a little bit of familiarity with Taylor series enables us to take the forward difference and the backward difference and come up with something better, radically better, the central difference approximation, 10 times the error convergence rate, that's error h squared. So it's an order of magnitude better rather than order h, but the same amount of work to be done. So a little bit of analysis, we can do something much better. But nonetheless, if you're using the central difference, forward difference, the central difference is better, but the only way to make h, or to make the error smaller, is to make h smaller. With central difference, the error will grow more rapidly, but we still have to make h smaller, to make that error smaller. Can we do something better? Can we do better than order h squared? Do something clever. So this is just what I've said. We can, using any of these previous approximations, we can get better and better approximations to the derivative using smaller and smaller step sizes. Can we do something better? Can we get order h cubed or order h to the 4 rather than order h squared? Problem with just relying on, say, central difference and just making h smaller and smaller, we run the risk of numerical round-off error due to very small h. So we'd like to do something something better. And similarly, if we're using one of these finite difference time domain solvers, like we saw a few slides ago with the aeroplane and the radar, the smaller h's, the more samples we need. The more samples we need, the longer it takes for the computation to run and the slower it takes to work out your radar cross-section return from an aeroplane. So you buy some commercial software and it takes a week to run. So we want to find ways of making the thing more accurate without just making h smaller. The central difference does that, but can we do something even better? Long-winded way of introducing what's called Richardson extrapolation. So the answer is yes. I wouldn't have asked the question if the answer wasn't yes. I wouldn't raise your hopes, only to dash them. So the answer is yes, you can do it. It's called Richardson extrapolation. How would it work? Well, let's take the following Taylor expansions. Okay, so this is what we've seen before. I'm just writing it in a slightly different notation. Here's f of x0 plus h, and it's the sum from n is equal to 0 to infinity of all the derivatives evaluated at the expansion point multiplied by h to various powers of n divided by n factorial. So this is just a neater way of writing the expansion we had before in terms of the sum. Similarly, the backward operator we can write like this. It's exactly the same, but with a minus 1 to the n term, and that gives us this alternating plus minus behavior. That's just a neater way of writing what we've seen before. And we can take that and take the top line away from the bottom line, divide by 2h, we get our central difference approximation. Seen that before. Now, imagine you got evenly sampled data. So you've got data sampled at step size h, lots of data, and there's a step size h between all the data. Well, that means you can now take every second data point, which are separated by 2h, can make a Taylor series based on that. We can make a central difference approximation based not on h, but on 2h. So to do that, we write a Taylor series expansion for points which are separated by not by h, but by 2h. You get this. Everywhere previously we saw a h, we now put in a 2h. Okay? And we take one away from the other on the left-hand side. Over here, we're going to get a 4h leading term, so we divide by 4h on the left at the bottom, and we get this. So we get a central difference approximation, which is equal to what's on the left, and a whole bunch of higher order terms, order h squared. So this is also a central difference approximation. Now at first glance, this is a really, really stupid thing to do, because we have data sampled with a step size of h, and we can make, as we saw in the previous slide, we can make a central difference approximation based on step size h. That's going to be accurate to a certain level. Now we go along and for some strange reason, we make a central difference approximation based on step size 2h, which is going to be worse because it's a bigger h. So it's going to be a worse approximation. Why would you do this? What's the point of doing this? Well, the point of doing this is, if you look at our central difference approximation based on step size h, the last terms on the right-hand side are the error terms. Okay, and they have a certain form. It's h squared over 3 factorial, third derivative x0 plus a whole bunch of stuff. On our inferior central difference approximation based on step size 2h, the first term on the right-hand side is again the derivative we're trying to approximate, and we have error analysis, or error terms. Now it turns out that the error terms here on this expression are very similar to the error terms in the previous one. This is just what I said. Let's put the error terms side by side. So on the top here, the first equation is the central difference approximation based on step size h. The bottom one is the central difference approximation based on step size 2h. The bottom one is inferior. The top one, on the right-hand side, we have the thing we're trying to estimate, f dash, plus an infinite number of error terms. On the bottom, we have, on the right-hand side, the first term is the thing we're trying to approximate, plus an infinite number of error terms. And the error terms on the bottom one are bigger than the ones on top, because it's inferior. But look, they look very similar. The leading error term on the bottom one is equal to the leading error term on the top one, just multiplied by 4. Same thing. On the top, we got h squared over 6, 3 factorial. The third derivative evaluated at x0. On the bottom, we have h squared over 6 multiplied by the third derivative at x0, just multiplied by an extra 4 times. What should we do? Anybody got any bright ideas of what should we do? What did we do to get the central difference approximation? How about you, NUIM? Any ideas? What should we do here to get something better? Well, in the central difference approximation, we had a forward difference approximation and a backward difference approximation. We added the two together and we cancelled some of these error terms. In this case, we can't quite just add them together because the leading error term on the top and the bottom aren't quite the same. But if we take the top one and multiply it by 4, the leading term, the top equation, just multiply everything by 4. The leading term on the error will be 4h squared over 6, the third derivative. It's exactly the same as the leading error term on the bottom. So if we multiply the top equation by 4 and subtract the bottom equation, what do we get? Well, multiply this by 4, take away the bottom equation, do it on both sides. We get, well, this is what we get on the left-hand side. On the right-hand side, we'll have 4 f dash x0 minus f dash x0, which is 3 f dash x0. And the beautiful thing is the first term in the errors cancel. So this will be 4 minus 4. This goes away and we cancel out. And we get this. The leading term in the error is now no longer h squared, it's h to the 4. We cancelled h squared term with the h to the 4 term. We can divide across by 3 and we get that this construction called Richardson extrapolation will be equal to f dash x0 minus some error term here. And the error term we see is h to the 4. That's much better. We started off with forward difference. That was order h error. As h gets smaller, error decreases by h. We came up with its central difference. That was order h squared, which means as h gets smaller, the error gets smaller by h squared. And now in this new formula, as h gets smaller, the leading term in the error is h to the 4. So the error gets smaller by h to the 4. 2 orders of magnitude better than h squared. Okay, so this is, as h gets smaller, this is going to, the error is going to get smaller much more rapidly than central difference. price we pay is that the computation is a little bit more complicated. It's slightly more expression, slightly more work to do, but certainly well worth it in terms of the overall error. So the error is order h to the 4 is given by that. That's the leading term plus an infinite number of terms. And we can also apply Richardson extrapolation to our estimate for the second derivative, or similar analysis. We get that. Okay. Let's do a very quick example. We have a function given in tabular form. Perhaps this is some output from a circuit, and we want to work out, like our circuit example, the current flowing through a capacitor or something like that. We have a value x at 0.6 up as far as 1. We have f of x corresponding. We don't know what f of x is, because we can't differentiate it. And we would like to work out an estimate for the first derivative at x is equal to 0.8. And we'd like to work out that estimate with error order h squared, and order h to the 4. And then the second derivative equivalent. So in order h is equal to 0.1 in this particular case, because the samples are spaced out by h is equal to 0.1. So in order h approximation is the forward difference approximation. It's equal to f at 0.8 plus 0.1, which is f 0.9 minus f 0.8. Going back to our table, the data, f of 0.9 is this, f of 0.8 is that. Here's f of 0.9, here's f of 0.8. Take one away from the other, divide by h, you get that. That's an estimate for the first derivative evaluated at x equals 0.8. It's going to be accurate to order h. A better estimate for this sample data is a central difference approximation, where we use f of 0.8 plus h, f of 0.8 minus h, divided by 2h. And we get this. So quite a difference, 4.995. This, we're confident, this will give us an estimate of the first derivative correct to 0.0 and 0.01. Because h is 0.1, so h squared is 0.01. And then order 0.0, so order h to the 4, we can use Richardson extrapolation. And Richardson extrapolation just has, uses function values at x plus h, x minus h, x minus 2h, x plus 2h, added together in a ratio 1 minus 8 plus 8 minus 1, and divided by 12h. Use the formula. That is 4.856. And this is the numerical estimate of the derivative that we're most confident in. It uses all the data. Similarly, for the second derivative, we can use central differencing. Turning to a central difference formula, we get that. Or we can use Richardson extrapolation to get a better estimate to order h to the 4, 21.76 rather than 21.8. So this last one is Richardson extrapolation applied to the second derivative. This is Richardson extrapolation applied to the, so this is central difference applied to the second derivative. Okie doke. That's the end of that handout. Has anybody got any questions for all of that? How about you, Manuth? Any questions? Okay, I make it 15:22. I propose we break just for 8 minutes and come back at 15:30, because everybody just needs to don't lie down for a bit. Okay, so let's come back at 15:30 and we'll do we'll crack on from there. Okay, I seem to have lost my webcam there, guys. I'll try it again. Okay, so I'm having trouble getting my webcam going for some reason. I'll keep on trying. Oh, there we are. I'll put it down here. Okay, there I am. Okay. Good. So let's crack on. Where were we? We're going to do ordinary differential equations. So what's all this about? Well, an ordinary differential equation, let's start with a very simple one. First order ordinary differential equation usually appears in the context of what's called an initial value problem. So what does it mean in English? It means we have some unknown quantity, some physical quantity, we'll call it y, which is a function of some other independent variable. So some physical quantity, y, it might be a voltage or a current or a speed or a force or any a component of a force, or some physical quantity, and it depends on some other independent variable. So typically it might be, that independent variable might be some dimension, some space, or it might be time. So it could be voltage as a function of time. It could be temperature as a function of space or something like that. So typically either the independent variable is usually denoted as x to denote some spatial dimension, distance in some particular direction, or t for time. Okay. So we've got y is the unknown quantity, the thing we want to work out, and it's a function of trying the webcam again there, guys. So we have y is a function of x, some unknown quantity, we'd like to work it out. It's a function of either x or perhaps it is a function of t. So rather than have needless duplication, rather than saying for the rest of the slides y is y of x or y of t, let's just make a decision. I will derive everything I do in terms of y being a function of x in spatial dimension, but everything I say holds for y as a function of t. Good. So in addition, what's an initial value problem? An initial value problem gives us an initial value to help us solve it. And it tells us this particular thing you're trying to work out, y, some physical quantity, we're going to give you some rules to tell you how to work it out. And in addition, I'm going to give you some initial information. I'm going to tell you that at some initial position, again, for the rest of the notes, we're going to assume y is a function of position, but everything I say holds for time as well. Y at a particular initial position, x0, we know the value. We don't know what happens after x0, but at x0 we know exactly what's happening. So that's the initial condition. So value of y at other positions other than the initial condition, you have to work them out. You're given the initial condition exactly, and you have to use an ordinary differential equation to work out what happens elsewhere. So an ordinary differential equation, generically, we can write it like this. We have an initial condition, y, the unknown quantity, evaluated at this initial spatial coordinate x0 is equal to some value. That value is, we call it y0, some value, some numerical value. In addition, we're given some rule for the derivative of y. Okay, so this is where nature plays tricks on us. Nature never tells us that the temperature in a room takes on this functional form, or the speed of this projectile takes on this functional form. Instead, nature's rules tells us nothing about y, but it's often couched in terms of what happens to the derivative of y. It tells us that the derivative of y, so the derivative of the temperature or derivative of the speed, is equal to something. Okay? I don't know why nature does it. Nature is just a bit of a tease. It doesn't like telling us exactly. It tells us this implicit way of approaching problems. So we've got some information on initial condition and then some rule. It tells us that the derivative of y, first derivative of y, for the first order ordinary differential equation, is equal to some combination of x and y. So it's given in terms of the input x and the output y itself. We'll do some examples. So note, we are not explicitly given an expression for y. That would be too easy. Nature doesn't like us particularly. Nature likes to play tricks. It doesn't tell us what y is, but instead it tells us what the derivative, the rate of change of y is at some generic input x. So it tells us at some point x, the rate of change of y at that input is some function of x multiplied by, combined in some way with the output at x, y itself. This is even more complicated because it means f here is given in terms of the independent variable x, which we do know, and the output at x, which we don't know. It's even more convoluted and combined. So the rate of change is given by this function f, and we'll see some examples of this now in a second, given in terms of x, the input, which we do know, and its value, the value of y at x, which we don't necessarily know. Let's do a very easy example just to get the ball rolling. Here is it's very simple ODE, very simple. There's some unknown quantity y. At the input 0, it takes on the value 5. Also, we're told that its derivative with respect to x is equal to x squared. We don't know what y is, but we do know everywhere its derivative is equal to x squared. This is the simplest ODE you can possibly do. So let's solve it. So it's the form we saw before, where f of xy, this thing on the right here in the second equation, is, while f in general is a combination of x's and y's, here in this particular example it only has an x. So it's f of x is given in terms of x alone. So the derivative is given purely in terms of the independent variable x. So we must find a y such that dy dx equals x squared. That's the challenge. That's the puzzle we have to solve. We have to find some function y such that dy dx is equal to x squared. So this is very easy to solve. We can do this by direct integration. Well, if dy dx is equal to x squared, y of x must be equal to x cubed over 3 plus a constant. Very easy. I told you this is the easiest one, the easiest possible ODE, and it is. It's very easy to solve. If dy dx satisfies this, y must satisfy something like this. Because when you take this expression x cubed over 3 plus c, differentiate it, you're going to get x squared. C is hugely important. Never forget the C. The C is hugely important. The answer to this puzzle is not yx equals x cubed over 3. That's not the answer. The answer is x cubed over 3 plus a constant, because there's an infinite number of possible functions, an infinite number of possible answers. Okay? To this, the second equation here, d dxy equals x squared. An infinite number of possibilities, all separated from each other by this different constant. Okay? So what we need to do is find the particular solution that has this form, x cubed over 3 plus c, but also satisfies the initial condition, and that will give us a unique answer. So to get a unique answer, we use the initial condition. It tells us that y at 0, that's going to be 0 cubed over 3 plus c, and our initial condition says this must equal 5, which gives us c is equal to 5. Now we have a unique answer. Now we know the solution to this ordinary differential equation is x is equal to x cubed over 3 plus 5. Okay? And we can check. This satisfies the initial condition because y of 0 is 0 over 3 plus 5, or 5, which our initial condition is right. And when you differentiate this, you get dy dx equals 3x squared of 3, which is x squared, which is right. So this is the correct answer. Okay. So here's a picture of what's been going on. The blue curve here underneath is x cubed over 3 plus 5. And what we see is that our initial condition was y of 0 equals 5. So when x is equal to 0, the output equals 5. This is the red dot down the bottom left here. Initial condition satisfied. And what the ordinary differential equation told us is that for a generic point, a generic input x, which is on the curve, x, here's y of x, point, some dot on the curve here, the tangent to the curve at this point, the slope of that tangent must equal x squared. That's what the ordinary differential equation, dy dx equals x squared, means. Okay, dy dx equals x squared. That means the solution, the thing here in blue, for a generic input x, a point on the curve, the tangent at that point on the curve has a slope, and the slope of that tangent is equal to x squared. So this point x is roughly 1.75. The slope of this tangent is roughly 1.75 squared. Down here, at x equals 1, the slope of the tangent at this point would be less severe. The slope would be 1 squared, or 1. So you can see the slope as x increases, the slope of the tangent becomes more and more severe. It becomes. The reason I show you the picture is because it's important to understand this picture if you're going to understand the numerical methods for solving ODEs. Okay, so pretty straightforward. Let's do a more complicated example. Here is another ordinary differential equation. It says we have some unknown function y. Don't know what it is, but we do know that at the input 2, its output is equal to 10. Okay, so that little piece of information, coupled with the differential equation itself, that the derivative of y of x is given by y of x over 2. So this is a function such that the rate of change at an input x is equal to the output y of x over 2. So in this case, the right-hand side here, generally given by f, some function of x's and y's, isn't given in terms of x's. Here it's given purely in terms of y. So in other words, there's a function y, and its rate of change at a point x is equal to the function output itself. We'd like to solve this. So we must find a y such that at every input x, the rate of change of y equals half the output of y. In other words, dy dx equals y over 2. And again, we can solve this very easily. So do we know of such a function? Well, just by inspection, we know, for example, that e to the alpha x satisfies the derivative of e to the alpha x is equal to, I should say, alpha e to the alpha x. Another mistake, oh my god, change that. That should say alpha e to the alpha x. And so y of x is equal to e to the x over 2 will satisfy e dx y of x will be equal to a half e to the x over 2 plus c, which is a half y of x. So something of this form, a function y of x satisfying this form here, will satisfy the requirement that its derivative is equal to itself multiplied by a half. Okay? So again, there's an infinite number of terms, infinite number of functions that could potentially satisfy this. Okay, because they all differ by c. Okay, so different c's will give us different outputs, but they all have this generic form. How do we work out the particular value of c? We know that for the particular input y is equal to 2, the output should be equal to 10. So when y is equal to 2, we have output is e to the 2 over 2, or e to the 1. E to the 1 plus c must equal 10, which means 1 plus c must equal log 10, which means c must equal to log 10 plus 1. So our particular solution is e to the x over 2 plus c, where c is given by this expression here. We can simplify that. E to the log 10 is just 10. So we get 10 times e to the x over 2 minus 1. And this is our solution to the ordinary differential equation. Okay? So this is another example. It's an ordinary differential equation of the type that we want to solve, but it's an easy one because we can solve it analytically. We don't need numerical methods. And again, here's our picture. The blue curve here is the actual answer, e to the x over, there's a 10 times e to x over 2. We see at the input 2, it has output equal to 10, so its initial condition is correct. Y of 2 is equal to 10. And we see for a generic point x, which is on the curve, the point x, yx, it has a tangent, and the slope of that tangent is equal to y of x over 2. That's what the differential equation means. The slope of this particular tangent here is equal to this value y over x over 2. So in other words, for example, the slope of the tangent at the initial condition, when x is equal to 2, y of x is equal to 10. So around this initial condition point, there'll be a tangent, and the tangent would have slope 5. Okay, that's the picture. Again, the picture is important because if we want to solve this numerically, it's useful to have the picture. Okay. Let's do a more complicated one. This is the most complicated one we have yet. We can still solve it analytically, however. Here is an ordinary differential equation that satisfies y of 10 equals 2. And that's the initial condition. And its derivative is given by, well, you take the function y, its derivative is equal, its derivative at a point x is equal to y of x, whatever the output is at x, we don't know what that is, multiplied by 2x plus 3. So for a given input x, we know what 2x plus 3 is. We don't know what y of x would be. But if we did know what y of x would be, we can multiply it by 2x plus 3, and that would give us the slope of the tangent. In other words, dy dx. So this is a real riddle. We have the derivative of y given in terms of y itself and given in terms of the inputs. So it's really convoluted, mixed up problem. Okay, so a bit of a chicken and egg because we can't, if we knew y, we could work out dy dx, but dy dx is given in terms of y, so it's a circular kind of thing. How do we solve it? We can use a technique called separation of variables, which is a standard technique for solving certain classes of ordinary differential equations. We get dy dx is equal to 2x plus 3 multiplied by y. That's our ordinary differential equation. Let's put all the y's on one side, let's put the x's on the other side. So divide across by y and multiply across by dx. We get 1 over y dy is equal to 2x plus 3 dx. Integrate both sides. We integrate the left with respect to y. We integrate the right with respect to x. Well, the integral of 1 over y with respect to y is equal to? The answers? What's the integral of 1 over y? Natural over y. Thank you. And the integral of 2x plus 3 will just be x squared plus 3x plus a constant. So this is log of y plus a constant, and over here we get x squared plus 3x plus a constant. And we can take the constant on the left over to the right, combine the constants into a single constant c. So if the top equation holds, that means y is some function such that log of y is equal to this x squared plus 3x plus c. Take the exponential of both sides. It tells us that y must be of the form e to the x squared plus 3x plus c. How do we work out c? The initial condition tells us that when x is equal to 10, y must be equal to 2. Therefore, e to the 10 times x, was it? What was the answer? The x squared. E to the x squared is e to the 100 plus 3 times x, 30 plus c is equal to 2. And when you work that out, it gives us c must equal to the natural log of 2 minus 130. And so, therefore, e or y, the answer for y is equal to e to the x squared plus 3x plus the constant, and the constant is given by that. There's one more slide, French guys, and then I'll let you go, okay? So I know you have to go to another class. Simplify that, e to the log 2 is equal to 2, so that becomes a multiplicative term too. And we can check our answer. We can check that y of 10 is equal to 2 just by putting x is equal to 10 in here. We get 2. This becomes e to the 0. 2 times e to the 0 is 2. And we can check that dy dx satisfies 2 times, using the chain rule, 2x plus 3 times this. So we get 2 times e to the x plus 3x minus 130, which is y. So this is just equal to this. Okay. So this is just a check. So this is how you solve that ordinary differential equation analytically. And again, here's our picture. The blue curve here is the actual answer that we just got. We can see the initial condition when x is equal to 10. Output y of 10 is equal to 2. And then for a generic point, x takes on the value y of x, and the slope of the tangent at this point is equal to y of x, which is equal to, in this case, roughly 10, multiplied by 2x plus 3. So the slope of this line here will be roughly equal to y of x, which is 10, multiplied by 2x plus 3 will be roughly 23 plus a little bit. So that gives us the slope of that line. Okay? So for various points x, the slope of this tangent will vary. It will always be equal to this. Okay, let's just take a break for 2 or 3 minutes because the French people have to go. So we'll break for 2 minutes, then we'll kick off again for a little bit. We should be able to do that. The methods are very easy. Once you understand what an ordinary differential equation means, so once you understand a picture like this, the actual numerical methods are quite straightforward. Okay? So the hard part really is understanding what an ordinary differential equation is telling you. So where do these crop up? Well, engineering examples turn up the whole time. These are analytical cases. In all cases here, we can solve it using direct integration or just by observation or by substitution, separation of variables rather. In all cases, we could come up with an answer without having to write a MATLAB code. It was easy. More complicated cases here is, for example, my colleague Melissa, who taught you guys signals last year, had a PhD module starting in April for PhD students on numerical techniques for RF circuits. So this here on the right-hand side is a typical piece of RF circuitry. You have lots and lots of inputs and outputs, and many thousands of interconnects and various devices and components on a device like this. And you would like to work out its time domain response. If you stick in a voltage input somewhere, what's going to happen elsewhere? And the whole system is basically described by a very complicated ordinary differential equation, or a series of linked coupled ordinary differential equations with the voltage here and the voltage over there coupled in certain ways. But basically it's a big coupled system of ordinary differential equations with respect to time that you have to solve. And you can't solve them by hand. You can't use the techniques we just showed, so it's too complicated. So you have to use numerical techniques to solve it. And so there's a lot of simulators you can buy on the market that does this for you. And again, this particular PhD module that we're running would look at kind of modern techniques for doing this more rapidly. Because you can buy a simulator that will do it for you, but a lot of these simulators will take you a week to run. The larger the problem gets, better resolution you want, the longer you have to wait, which is very good. So there's obviously a real research problem in how to get good answers by solving these differential equations numerically, but solving them in a rapid and in a computationally clever way. And that's what this all that line of research is about. Okay? So we needn't concern ourselves with that, other than just to note that this is a useful thing to learn for electronic engineers. It isn't just something for mathematicians, it's for electronic engineers as well. And you can go and make lots of money. If you guys can understand your ODEs, you can go and design better software, sell it, and then retire when you're 35. Do whatever you want to do. So let's look at a numerical method for solving this stuff. The function f. So what is the function f? Remember, we have dy dx in our ordinary differential equation is given by some combination of inputs x and outputs y's governed by some function f, some combination x, y. Okay. So in the last case, f was equal to 2x3 multiplied by y, I think. So in general, f might be a linear combination of x's and y's, or it might be nonlinear. Okay, so nonlinear ones are really more interesting. So what we do is, if we can't solve it analytically, what we do is we take a finite difference approximation to the derivative. We say dy dx, this function y, we don't know what it is. We don't know what it is, we can't look at dy dx. But what we can do is we can approximate dy dx in terms of sampled values of y, using the numerical approximation we did in the last handout. Forward difference, central difference, etc. Okay? And we can derive some equations. So we can say, here's y, we don't know what y is. We've been given some puzzle by nature, and nature has told us that the derivative is given in terms of some complicated combination of x's and y's. We don't know what the derivative is, but we do know that the derivative can be written using a forward difference approximation as, for a given input, we can write the derivative as y evaluated at the input plus h minus y at x divided by h. This is just our forward difference approximation with input. And we can rearrange that. We can say, therefore, just by taking h over to the left side and bringing y over to the left side, we can write y at x plus h in terms of y at x. Okay. And this gives us a hint, because we have an initial value. We know y exactly at one initial value. And this method here allows us, if we know y at some value x, we can work out y at some value x plus h in terms of y at x and the derivative of y at x. So this is the key to make progress. We're given an initial value. This finite difference approximation to the derivative tells us that if we know y at some initial value, x, we can work it out at x plus an by doing a computation like this. If we know y at x plus h, we can recursively apply this and get y at x plus 2h, y at x plus 3h, y at x plus 4h, and march the solution on in space. So if we call x0 is our initial condition, and if we say x1, use the notation x1 is equal to x0 plus a single h, then this formula here gives us the Euler estimate. Okay, and the Euler estimate, we denote by y hat 1, is our estimate for the actual function value y evaluated to x1. So there's the underlying answer, we don't know what that is. Y evaluated to x1 will be forever unknown to us. It's the exact answer. We call that y1. we can make an estimate for it, y hat 1. So the hat here symbolizes or signifies that this is an estimate. And we can say that y hat x1, our estimate for the output at input x1, is equal to y at x0, our initial condition, which has been given to us, plus h times the first derivative at x0. But our ordinary differential equation gave us an expression for the derivative, dy dx, in terms of this f thing. And f was some function of x's and y's, so it's some function of x0 and y0. And for our first step, where we have x0, because we know the initial condition is applied to x0, and we know the initial condition tells us the output at x0. So we have both of these things here. We can put them into f, and that gives us y dash. And therefore, we can approximate y not at our initial point, but at initial point plus h. Or again, using our new notation, rather than a little bit cumbersome saying our estimate at x1, we just call that y hat 1. So y hat 1 just means our estimate at input x1. Y0 just means our initial condition. It's our value of y at x0. Just for ease of notation. Once we have this, y1, we can recursively apply it. We can say, well, y of x2 is y of x1 plus h, which is equal to y at our initial point plus 2h. So we use our initial condition to get values or an estimate at x1, and we can do it the same trick again to get the value at x2, x3, and x4, and x5, and keep on doing it. And we can just do the same trick again. We can say our estimate of y at x2 is equal to our estimate of y at x1 that we've just computed, plus h times our derivative at y1, and this here is our estimate of the derivative at y1. Okay? We take our ordinary differential equation, the puzzle tells us that the derivative dy dx is given by this function f, which requires an input and an output. So we have input x1, we have our estimate of y1 from our previous step, we can plug these in, we get f. In general, we just march on in this fashion. What does this involve? We say at the nth step, or the n plus 1 step, we say the n plus first approximate output value, so y at xn plus 1 is equal to the previous approximation, plus h step size multiplied by our estimate for the derivative at xn. We do this for n equals 0, 1, 2, just keep on matching. Here's a picture to tell us what it is we're doing. So the purple curve here is the unknown underlying function, y. We don't know what that is. Okay? But just for relation, in principle we don't know what it is. Here's x0, here's our initial point. So we are told in the problem setup that at x0, the output is equal to y0. So we're given this red point, which is definitely on the curve. Okay, we're given that information. That information is exact. So our initial point, our initial estimate, y0, is just given by this initial estimate, and it's equal to y0 because this initial point is exact. So we can initialize our process exactly. Now, what do? We say that y1, well, what does y1 mean? Well, y1 means we take a step along the x-axis to h, of h to x1. So our next point of interest is x1. The actual value of x1 is equal to y1, which is the red dot on the purple curve. We don't know what that is. Instead, we make an estimate for it, given by y hat 1. And how do we get the estimate? The estimate is obtained. So the estimate is equal to our initial value plus h times the derivative evaluated at x0. The derivative evaluated at x0 is just the slope of the tangent at x0. So that term h times the derivative is equivalent to just taking the tangent at x0, y0 and traveling along the tangent a distance h. That's what that correction term h times the derivative means. It means we start off here, we assume that the underlying function, the purple function, is linear, and we travel along that straight line a distance h until we get to y hat 1, which is the lower of the two red dots here. So we see we've immediately encountered a little error, because the Euler approximation says we have the initial point exactly. We're going to assume that the underlying function is a linear function. In other words, it's a straight line. We're going to estimate the slope of that straight line by the tangent here and travel along that tangent a distance h until we get to a new point. And the problem is the underlying function is not a straight line. So we've been traveling along this straight line, a distance h, and all the while the underlying function is not linear, it's been curving away ever so slightly from us. So our estimate is y hat 1 and the actual answer is y1. Then what do? We repeat the process. We say we're now at x1, we would like to go to x2 and make an estimate for the function value at x2. The actual answer is y2. We don't know what that is. The best we can do is we can take the value x1, we can take the value y hat 1, which we do have. We can feed it into this expression here, f. We can just stick in x1 and y hat 1. We can feed it up here into this f function. That gives us an estimate for dy dx at this point. So in other words, it gives us an estimate for the slope of the tangent at this point. And we make the approximation that the underlying function is linear, and therefore we can travel along this tangent a distance h until we get to the next estimate. We get to here. Okay. And again, what's happened here is the underlying function is not linear, so we've been assuming it's linear. We've been traveling along the straight line to get to here, but the underlying function has been slowly curving away from us the whole time. Okay. Questions about that? That's kind of key to understanding all this. So it's useful to spend a bit of time looking at this and trying to understand it. We have an initial point, x0, we have an initial point, y0. Everything is exact at this point. With this initial x0 and this initial y0, we can plug them into f up here and get an exact answer as the slope of the tangent to the curve at this point. Everything is fine. Now here's where things start to go wrong. Things start to go wrong because we now say, let's follow this tangent a distance h until we get to the next point. If the underlying function y was a linear function, that would be exact, perfectly correct thing to do. But the underlying function, rather than having this tangent the whole time, the tangent is continuously changing and bending away from the tangent that we are following. So we follow this tangent, a distance h, and we've injected a small little error. And this is where the numerical part of it comes in. This is not an exact answer, it's a numerical answer. So the problem and the game that we have to play when we're developing solvers for ODEs is to come up with methods that minimize the gap between our estimates and the actual unknown real answers. No, that's a very good question, and we'll see why in the next point. Okay, so the question there is tangent at y hat 1, so the black line here passing through the slightly lower of the two red dots. That's a tangent. It's a straight line going in a certain direction. And the question is that tangent equal to the tangent of the actual curve? So in other words, the tangent passing through the actual point y1. And the answer is no. No, it's not. It's slightly different. We'll see in a second. Okay? So let's see where the error comes from. So at the start, everything is fine. We're given an initial condition. And the initial condition tells us that at input x0, the output is y0. So we're exactly right, no errors. We have x0, we have y0. We can put them into this expression f, which combines x's and y's in some way. That gives us this slope at x0, y0. It gives us the slope of the tangent. And it gives us that slope exactly. We know exactly what that slope is. So everything is perfectly exact at that point. We know y0 exactly, and we know the slope of this tangent exactly. It's given by this f of x, y, y0. The problem then happens because using the Euler method, we follow this tangent a distance h along the x-axis. After one step, we have an error because we've followed a straight line when the actual underlying curve has curved away ever so slightly. So we've introduced an error. So y1 hat is no longer equal to y1. And this presents a further problem because now for the next step we have to work out the tangent to follow for the next step. So we take x1 and y hat 1, we plug it into the formula, we get f of x1 y hat 1, and that gives us our estimate for the tangent to follow between x1 and x2. But the problem is because y hat 1 is incorrect, it means f of x1 y hat 1 is now no longer the actual tangent, it's only an estimate for the tangent. So not only is our starting point here wrong, the direction that we follow is slightly wrong as well. So there's two errors now. Our start point is wrong, and the direction that we head off in to get to the next point is slightly incorrect also. Is your question. So we follow this slightly incorrect tangent. We get to point x2 and we get y hat 2, which is now slightly even further away from y2. Okay? So our error is growing at every step. We're starting off at every step, we're starting off at the wrong point compared to where we should be. And the direction, the tangent we're following is slightly incorrect because we're taking the tangent, the formula we're using is this f expression here. It requires knowledge of x and y. We have precise knowledge of x, but we only have approximate knowledge of y. We use y hat rather than y. So this f function, which tells us the slope of the tangent to follow, is giving us a wrong steer as well. It's heading us off in a slightly wrong direction. So the key point there is we start off perfectly well, but we diverge slowly over time. These errors creep in, and these errors grow after a while. And the game is to come up with a method to ensure that we minimize this growing error the whole time. It will appear, it will grow, but we want to make it grow in an acceptable fashion. So it turns out the Euler method is okay. But it does introduce an error, and that error grows at a rate which is a little bit too fast than what we would like. Okay? So let's analyze the error in the Euler method. Let's try and do the first step exactly. That's what the first step involved. The first step involves starting off at x0, the precise knowledge of y0, precise knowledge of the tangent at that point, and then trying to get an estimate for y1. So this is what we did. In theoretically, we start off at x0. We would like to get the output at x1. And theoretically, what we could do is we can say the output at x1 is equal to the output at x0 plus the integral of dy dx over this entire region between x0 and x1. Okay? To do that, you can prove it. Well, dy dx times dx just gives us dy. So dy dx integrate with respect to dx just gives us y at x1 minus y at x0, which gives us y at x0 plus this minus this gives us y at x1. So this is exact. So if we could integrate dy dx exactly through x0 to x1, we could do this step exactly right. The problem is working out dy dx integrating exactly in this interval involves knowing the tangents not just at the start point, but at all points between x0 and x1. Okay? We don't. We only have it at the start point. If we had the tangent at all points between here and here, it would be fine. But we don't. We only have it at the start. So what does Euler do? So this is exact. If we could do this exactly, it would be right. But the problem is we don't know dy dx explicitly in terms of x. We have it in terms of x and y. So we have a chicken and an egg problem. In order to get y on the left-hand side, we need to integrate something involving y. So we're getting y in terms of itself, which is an implicit definition of y. So we can't explicitly. So we're given dy dx in terms of y itself. We're trying to get y, but we're given y in terms of y, so we can't use this. So the problem is we need to know what y is. To go from x0 to x1, it isn't enough to know y at the start. We need to know it at all intermediate values between x0 and x1. And we don't. We only know it at the very start. Okay. So what numerical schemes do, like the Euler scheme, it says, in going from this step to x0 to x1, to do it exactly, we need information about y at all points, a continuous, an infinite number of continuous points between here, and that's obviously impossible. So a numerical scheme instead says we'll estimate y at a discrete, finite number of points in this interval. The best we can do. What does the Euler method do? Well, the Euler method takes, this is, if we could do this exactly, we'd be laughing, this integral. But the problem is we can't do this integral exactly, because to do this integral exactly, we need information about y. We don't have information about y. We only have information about y at the very start of this interval. So Euler says, well, try that. Let's just take the value we have at the start of the interval, x0, y0, and do a one-point integration, like a midpoint integration. We say this is the value of the function at the start of the interval, x0. We have this information. The interval is of width h. So we take the function value at the start, we multiply it by the width of the interval, and that gives us an estimate for this area. So this is just like the midpoint rule in integration. So it uses a simple one-point integration to approximate this, kind of like what the midpoint rule does. But the midpoint rule is in the center. Euler does it at the start, because the start is where it's information. So this is the Euler rule we just were applying previously. Y at x1 is equal to y at x0 plus h times the derivative of 0. It's similar to the midpoint rule, but we're using information, the sample point is at the start rather than. Okay. Let's do an example. Euler's method. Let's take a step size h is equal to 0.1. Let's approximate the solution to this differential equation. This is a differential equation. It tells us that we have some unknown function y. If we knew what y was, we could differentiate it. We would get the square root of y back again multiplied by x. We don't know what y is. We're told there's an infinite number of functions that have this derivative. So in order to make this unique, we're told that y of 2 is equal to 4. So give me the specific function that not only satisfies this condition on the derivative, also has y of 2 plus 4. And do it between input between 2 and 3. So the actual solution, I'll leave you to work it out yourself by separation of variables. You can show that y of x, the actual solution to this is y is equal to 1 plus a quarter x squared squared. Okay? And you can check that, take dy dx of this, you're going to get something of the form square root of y, which will just be the term in brackets here without the 2, an extra x term. You can convince yourself about that. And try and do it by separation of variables or whatever you want to do it. So I wrote a MATLAB code, and we'll talk about the MATLAB code maybe on Tuesday to do this. So we start off at our first step. Our first point x0 is 2. That's our initial condition. The exact solution at x equals 2 is 4, where 2 is equal to 4. So our exact solution is 4, and our Euler approximation is 4. So we take the exact answer. Our error is 0, our relative error is 0. Okay. Then we take a step. And the Euler method says that the step is y1 is equal to y0 plus h times f evaluated at x0, y0. Well, x0 is our initial point is 2, so we get 2. y0 is our initial output value, which is 4. So square root of y0 will be 2. 2 times 2 gives us 4. H times 4 will give us 0.4. So our other step will be y0 plus 0.4, or 4.4. Maybe I should have written that out explicitly, but how we go from 4 to 4.4 is as follows. We take this, x0 is 2, y0 is 4. We plug those values in here to get dy dx equals 4. We multiply it by h, which is 0.1. This is 0.4, and we add that to the previous output to get 4 plus 0.4 over 0.4. Our exact solution, if we were to use this formula here at the bottom of this page, is not quite 4.4, it's 4.4205. So that's our error. Our relative error is the error divided by the value of y, just to see how accurate we are. The relative error is a better indicator because an error might look very small, but a very small error in terms of a very small answer is actually quite a big error. You know? So I could tell you that I have an error of 0.1. The exact answer was something, my estimate was something else. The error was 0.1. That sounds impressive until you find out that the actual answer we're trying to get was 0.00000. And all of a sudden 0.1 error and the actual answer was 0.0001. It's actually huge. So we need to do a relative error. We need to ask not only how big the error is, we need to ask how big is the error compared to the thing we're trying to get. Because an error of 0.1 is pretty good if the actual answer was 10 million. It's not so good if the actual answer was 10 to the minus 8. The relative error here is important. The next step, our input goes from 2.1 to 2.2. We do the same trick again. We work out our derivative at 2.1, so x is equal to 2.1. X is equal to 2.1, so x1 is 2.1, y1 is 4.4. We put those in here, we get 2.1 multiplied by the square root of 4.4. That'll give us some answer. Multiply that by h, and we add that to 4.4 to get 4.8405. And that is our estimate of y2, the output at x2. The actual answer is this, and see our error has grown from here to here, it's pretty much doubled, and so on and so forth. We can do this by hand if you want to. It's a good exercise. I suggest you do this by hand just to see where these numbers come from. I generated this using a MATLAB code, but useful to do it by hand just for the first couple, just so you can convince yourself you know where these numbers are actually coming from. So you keep on going, and we see after 10 steps, we've gone from our initial condition where we had no error to x is equal to 3, and the relative error has grown to 3.27. I think this is in percent, probably. I think it's a percentage there. Yeah. 0.34. 3%. Okay. So we see the error grows. Okay. We start off with exact, and because of the limitations and in the finite difference approximation to the derivative, we introduce an error, and that error grows and grows and grows. Let's do one more method. Then you can do your assignment. That's the Euler method. It's okay. It has the advantage of being really simple to do. It's very simple to work out. There's the little potted algorithm then. Here's a little potted algorithm. Very easy to code up. We start off with y0 and x0, and we do a for loop for the number of steps you want to do. And at every step, our new output value is equal to our previous output value plus h multiplied by an estimate of the derivative at the previous value, which is obtained by taking f, whatever f may be, plugging in xn, which we do know, and our previous estimates y hat. Plug that in there, we get a number, we increment and move on. We code this up in 3 lines of MATLAB, 4 lines of MATLAB. So it's very easy to code, and it's reasonably good. It could be much better. So it's got an error of pretty much order h. So the error kind of grows with h. So to keep the error small, we can make the error small by making h smaller. So let's go back to our example. Here, after 10 steps, we've gone from x is equal to 2, where we had precise information, to x is equal to 3, and we've introduced an error of about 3%. Okay? Say we wanted to make that error smaller. Say we wanted the error to be 1% or 0.1%. We can definitely do that. We just make our h step smaller. Rather than taking a step of 0.1, we could take a step of 0.01. Okay? This would definitely be more accurate. We would definitely reduce the error by the time we got to 3. But rather than taking 10 steps, we would take 100 steps. So the code would take 10 times longer to run. So the Euler method is good. We can kind of control the error. but we can control the error by making h smaller. Making h smaller slows down everything. It's 10 times through. And again, you have one of these RF circuits we saw previously with many thousands of components and things. You really want that thing to work as quickly as you can. You want it to be quick. So Euler is okay, but it's not particularly well used as a concept. How can we improve it? Well, the obvious way to improve it is to use what's called the predictor-corrector method, which is best explained graphically, but let's do it mathematically first of all. Here's the Euler method. It says that we were at step n, we had estimate yn. We could make an estimate for the derivative by taking xn and y hat n, sticking it into f and multiplying by h. And we can make an estimate then for output at the next step, yn plus 1. So the predictor-corrector method, or the improved Euler method, says, well, hang on, rather than taking this as being our next estimate, let's just use it as a provisional estimate. Let's just not keep it. Let's just look at it for a second. What we say is, let's use it to make a better estimate of yn plus 1, according to this formula here. Where does this formula come from? Best to explain with a picture. Here is our first step. Here's x0, here's x1. So our first step, we have precise information. x0, y0, we precisely know the slope of the tangent at that initial point. And what Euler does is it makes the assumption that this curve does not deviate from this tangent, and it follows the tangent the distance h to end up here at y1. And obviously, the actual curve does deviate, hence the error. So Euler follows this tangent, ends up here. The reason there's an error is because for the actual curve in purple, the tangent is continually varying in this region. It only starts off as this tangent. It ends up facing a completely different way. So the predictor-corrector says, well, rather than saying during this entire interval that this curve can be approximated by a straight line with this slope, let's look at the tangent at the start of the interval. Let's predict the tangent at the end of the interval. And let's use the average of these two slopes. Let's say that the average tangent in this region is equal to the tangent, the slope of the tangent at the start and the slope of the tangent at the end, averaged. Okay? So Euler, kind of pig-headed, it just uses the tangent at the start and says, I'm assuming that the tangent does not change. And he introduces an error. The improved Euler says, well, actually, I'm aware that the tangent does change over this region. So what I'm going to do is I'm going to take the slope of the tangent at the start. I'm going to predict the slope of the tangent at the end by using the Euler step. I'm going to say that over this interval, the tangent is not equal to the tangent at the start or the tangent at the end. It's equal to the average of the two of those. And I'm going to go back to my first step, and rather than following the initial tangent, I'm going to follow the average tangent instead, which is this line here. Okay. The predictor-corrector does two things. It does the Euler step to get to here. It then takes this to estimate the tangent at the end of the interval. It then says the overall average tangent over the interval has an average tangent equal to half this plus half this, and follows that average tangent. It goes back to start, and rather than following the tangent we did the first time, it follows the average tangent. And we see we end up at y1 hat here rather than y1 hat star, which is closer to where we want to be. That makes sense? Or graphically makes sense. You see where the equation comes from. We take y at a general step. We go from yn to yn plus 1 by taking an average of an estimate of the slope of the tangent at the start at xn plus the slope of the tangent at the end of the interval, which is obtained n plus 1 and our Euler estimate to give us an estimate for the output at the end. This is an estimate of the slope at the start. This is an estimate of the slope at the end. Add them two together and multiply by half. And this gives us an average tangent instead. And we follow that. We can think of doing this. Rather than following our initial tangent, we follow this improved tangent instead. Okay, because there's nothing sacred about this initial tangent. The tangent is continually varying in here. So this initial tangent is wrong. this tangent at the end is wrong, but by taking an average, we're going to get a tangent which is somehow closer to the average. Alternatively, we can think of it as following. An alternative way of thinking of it, equivalent, is that we start off following the initial tangent, or not the entire step h, but only h over 2, and then following this estimate of the tangent at the end for the second half of the interval. That's an equivalent way of thinking about it. Two different ways. They're both the same. Let's do some sums. Predictor corrector, I'll let you work out this yourself, just the first couple of lines. Don't do it all. Let's go from n equals 0 to n equals 1, and maybe from n equals 1 to n equals 2 by hand, just to convince yourself. And we see that the predictor corrector approximation, when we start off with a 0 error because it's the initial condition, we get after one step, we get to 4.4202, which is really close to 4.4205. Percentage error, but these are percentage error, 0.0058%, which is much better than what we had before, 0.0058, rather than 0.46. So using Euler, after a single step, we had a percentage error of 0.5%. Using predictor corrector, which is a similar amount of work in terms of your coding, a single step, rather than 0.5% error, we have 0.005% error. So much, much better. Okay. So it turns out that the predictor corrector is order h squared, while Euler is order h. Okay, let's leave it there, I suggest. That was giving you enough to at least start part 4 of your assignment. We're going to do the Runge-Kutta method next week. There's only about 2 slides, but we're too tired to do it now. Runge-Kutta is just a variation on this theme of predictor corrector. Rather than predicting at the front and the end, it makes several predictions throughout the entire interval and uses those. So we'll do that on Tuesday, and then we'll move on to multi-step methods. We'll finish this on Tuesday, but now you have enough to start your assignment at least. Okay. Okay, I shall see you all on Tuesday. I'll see you guys on Monday. Maynooth, I'll see you guys on Monday as well at some point. Looking forward to seeing all your good work on Monday, so make sure you have something to show me. So we'll leave it there, and could everybody in Maynooth please log off when you get a chance, because I need to finalize the recording here so I can put the